All right. So good afternoon if you're in the East Coast. Welcome to the Rising Star Symposium series of the Special Interest Group in AI and ML in Security. We are a special interest group within technical community of cognitive networks, which sits within the IEEE ComSoc. I am Shubha Subbalakshmi. I'm a professor at the Stevens Institute of Technology in the Electrical and Computer Engineering Department. We have been a SIG for a long time, and we've had a bunch of activities. We recently joined by 3 other new VCs. So they are, I guess I'll let them introduce themselves. We can maybe start with Debashri and then work from there.
Yes, yeah. Hi, everyone. So I'm Devashri Roy. I am assistant professor at the University of Texas, Arlington, and with the computer science and engineering department. And yeah, so this is our initiative from the special interest group, and we are very happy that you are all here.
Okay. So maybe Hanif next.
Yes. Good afternoon to all those who have in East or Midwest, East Coast and Midwest. Hanif Rabari, Department of Cybersecurity and affiliated with the Department of Computer Engineering at Rochester Institute of Technology.
Hi, welcome everyone. I'm Dr. Moinul Hussain from George Mason University. I'm currently with the Cybersecurity Engineering Department.
Okay. Dola, who's also here, you can see her picture here. She is from SUNY Albany, and she cannot make it today. But let me quickly introduce you to the AI ML Sec. Maybe if you could go to the next slide. So right now we are about 468 members. You can find us on LinkedIn. You can search for the SIG AI ML Sec. In your LinkedIn, we have a group there, so you can just join there. Or if you would like to email one of us, our contact addresses are here. We've been engaging in a virtual seminar series since 2020, I think, with the first talk from Winspoor from Princeton. And since then, we've had quite a few series of talks in this. These talks, you can even see them recorded in the website you have in the SIG website, or you can also find us on the YouTube channel. So we are now expanding our activities by including this Rising Star Symposium series, and this will be our very first talk in that series. So at this point, I'd like Debashri to take over from here and then continue with introducing the speaker and the series and so on. Thanks a lot for being here, everybody.
Thank you, Professor Subha. So this series we thought about because I am right now just joined as an assistant professor this year, right? So when I got invited to be a vice chair of this group, and we are thinking about new ideas, what type of activities more we can do to contribute to the community or engage in our group. So we thought of why not to have like a platform for the candidates or like students who are graduating, who are the rising star for the future, and who are graduating or maybe doing postdocs and they want to pursue academia or like give job talks in next few months, right? Or we give them a platform to practice that, or to reach out to broader academic community, or even for industry who are also interested for industry. So it's like to intended to foster more mentorship and employment opportunities. We are hoping that in the audience will have some of the professors or the employers who are maybe looking for candidates, and the candidates can also practice their talks in, or maybe out like their research, right? Discuss more about the research. So yeah, so that was our vision and theme, and this is our first talk. And the logistics we are going to maintain the same logistics the way we did earlier for this group. So far we are requesting everyone to be muted throughout the talk, and if you have any question, please write in the chat box, but towards the end, if needed, we can also open up, like ask your questions directly. And anyway, we are going to moderate the questions at the end of the talk. But you can definitely write your questions in the middle of the talk whenever things comes to your mind. So with that, so today's our speaker is Dr. Chia-Yi Yeh, and she is right now postdoctoral associate in the Department of Electrical Engineering Computer Science at MIT, and she's also affiliated with the School of Engineering at Brown University. So she's working with Professor Muriel Medard and Professor Daniel Mittelman. She received her PhD and master's at the ECE department from Rice University, and she was working with Professor Ed Knightley earlier. So her expertise spans in many various domain of wireless communication systems, security, sensing, like millimeter wave, terahertz networks. So today we are going to we are going to hear from her about her research in terahertz links. So Chia-Yi, the floor is yours, and please feel free to share your screen.
Thank you, Dabershi. So first, a good introduction. I'm very happy to be here, being the first presenter for the series. And then this would indeed, it's kind of a practice talk for my future job talk, as I'm actively searching for faculty position this year. So today I'm excited to share with you our project in kind of reimagining how we can achieve security, combining our capability in engineering physical layers properties and network coding. So let me get started. So when we think about wireless link security, I think like two things would come to everyone's mind. So the first one is encryption. So you kind of say, okay, I'm gonna send this message, then that's encrypted, and then the message is should be secure, given that the eavesdropper has certain computational capabilities. And the second way is also known as kind of the physical layer approach. And then in general, so the way to achieve this is there is this Bob and Eve, and then by the discrepancy between the two, for example, SNR gap between the two, that we can encode our message in a way that the eavesdropper would not be able to decode the message. So the original formulation of this approach considers the channel in noise statistic, and then it's achieved in the long term, like in a syntactic region. So there's kind of a sense of the security is achieved in the average sense, and until it reached the asymptotic region. So then when we started this kind of project, what we are trying to achieve, it's like our vision, our goal is to come up with something, whether we can achieve something that has this nice, security. It's like that doesn't depend on eavesdropper's computational capability, and then it's not achieved only in a syntactic sense, that we can achieve also without kind of considering too much about the noise realization. So this is the scheme that we come up with, and so which combines engineering in the physical layer property and then network coding. So I'm showing on the right-hand side this transmission, as you can see from Alice transmitting to Bob. And then, so this scheme, so in the first place, we want to have a physical layer design. So as you can see, and then this fixed antenna radiation design exhibits radiation minima, such that there will be some locations where some of the channel is basically missing. And then the second step, we want to say each of the frequency, they're actually transmitting a different combination of messages. So then this becomes a linear system, so that if the eavesdropper doesn't obtain the whole linear system, she will not be able to solve the system. So then thereby achieve the security. So this is in a high level what we are doing, and then I'm going to get into more details in the following talk. So what we are trying to achieve here is that in a large spatial region, we can achieve what we termed blind region, that eavesdropper fails to detect one of the frequency channel, and then therefore we have a large and secure region. So what we demonstrated in this security scheme, some of the advantages is that we actually don't assume the eavesdropper's location. What we're trying to do is to provide a significant region that this scheme would be secure. And then, so we want this security to achieve kind of less dependent on the noise realization, but so we want to have a stronger physical layer argument that this security is achieved. And then the third one, I think this is a very interesting and unique property in security scheme, which is that our security scheme actually has a simultaneous improvement with data rate and security. So by that, I mean that when we increase more frequency channels, like more frequency bands, so for sure, our data rate is increasing, no doubt. And then secondly, because we can include more radiation minima in our design scheme, so then our blind region and then like the security also enhance together. So I hope this introduction give you some excitement going into this topic. So what I'm gonna do in today's talk is to kind of go over how we have developed this absolute security scheme, the different design elements. And then at the second part of the talk, I want to dive into like deeper how this radiation minima can be designed across frequencies for different addressing different challenges. Okay, so the project actually started with like three groups. So this is kind of a big behind the story, how this interesting project started. So we actually have 3 teams of people from Rice, Brown, and MIT, and then one is from wireless networking, one is from the perspective of physicists, and then one is a perspective from information theories. And then we want to kind of combine all the effort to for inherent secure high frequency link. So so it started with the information theorists saying, is it possible that in the wireless channel that we eliminate some completely eliminate eavesdropper's observation? We don't need total elimination. We just need you to eliminate some of them, part of the transmission. Because like if you can do that, we can do magic with that. So this is what the physicists in response. So of course, I mean, we know that in physics, right? So if you give me an antenna, let's say a linear array or a parabolic dish, there is naturally radiation minima, as I show in this example. So, and then you see those strong minima, and then expecting that if someone is located at those minima directions, they're actually not getting that part of the signal. So then another important thing is that this radiation minima actually shift with frequency. So it's not fixed at a location, it's a frequency dependent behavior. So I want to kind of emphasize that there is a flavor. When you see this is kind of, okay, it's something related to zero forcing. And I think there is, but I think our scheme is a more generalized idea than just than the conventional zero forcing. So for example, so in the zero forcing scheme, you kind of say, okay, I know where the eavesdropper is. So then I put the null there. I engineer my radiation minima there. But here we actually don't know where eavesdropper is. So this is like a very different threat model. And then secondly, so like when you do zero forcing, I mean, you cannot do it with all kind of antenna. Like for example, the parabolic dish wouldn't be able to, kind of direct its node to whichever angle that you want. But then for our proposed scheme, so we actually think this is like compatible with parabolic dish. And then the third one is for zero forcing security schemes, they typically concern with like this specific band transmission, but then our solution is more applicable to a wideband transmission. So what happens here is that we have this wideband transmission, and then we want to frequency channelize it. So I'm showing here this band, and then actually like we are chopping it up into Q channels, right? So the thing is that we want to have different operation in each of the channels, and then in physical layer, and then also without the message that we are gonna send in each of the channel. So first of all, we want the signal intensity to vary with frequency at the given location, right? So we are doing a frequency dependent operation, and then so everyone knows that this signal intensity would depend on like these factors, like how the transmit power at the transmitter Alice, and the channel gain, which is related to the path loss. And then the third part is your transmitter antenna gain. It's like this is the part that we are focusing on. It's like we want to engineer this antenna gain so that it has radiation minima, and then therefore a very low signal intensity in some direction, and then this should be a frequency dependent behavior. Okay, so the next argument, I think that it's also very like essential to our imagining of this security scheme, is that we want to establish an argument that the eavesdropper for any detector, because eavesdropper is a receiver, it's a detector, there exists something that is like a minimum detectable signal threshold. By that, we mean that below that threshold, eavesdropper cannot detect the signal at all. Because it's too small that there's certain fundamental limit to any detector that we build in the world, that once your signal intensity drops to that point, your detector cannot perform effectively. So this threshold, you can imagine it can depend on how you construct your receiver, its technology, the sensitivity of it, and then like which environment you are at, what kind of let's say ADC-TSC you are using. But I think like at a very generous analysis that we can think about the system is that because we are not living in a zero Kelvin world, so then we always have some background radiation going on. So that's related to the room temperature. And then because there is this, black body radiation background, that it should establish a minimum detectable threshold for any of the detector. So based on this idea of minimum detectable threshold, so we define our blind regions. So the concept here is like the blind, we define blind as this signal intensity becomes below this detection threshold. And then, so this blindness happens kind of frequency dependent, right? So in each frequency channel, in each frequency, it can be blind or not blind, depending on each of the location. Then we for the overall transmission, what would be the blind region? So that we define it as the locations where eavesdropper cannot detect at least one frequency channel. So it just have to miss once. And then essentially it's saying that, okay, it's okay. We only need the eavesdropper to miss one. So then the blind region for the total transmission is the union of blind regions per frequency. So here's what I mean by the right-hand side example. So you can see, we are transmitting in the main lobe direction where, this our receiver Bob should receive, all frequency channels like represented by this orange and green block. And then there will be some blind regions like associated with each of the frequency. For example, you can see, there are some shadows corresponding to the orange frequency. There are some shadows corresponding to the orange frequency. And then, so in each of these, like gray, orange, and green shades, like they are missing one of the message, and then it's a collective shadows here that constitute our blind region for the total transmission. And as you can see, if we have more and more frequency channel, it means that we can potentially include more and more shadows and blind regions in our security scheme, and therefore we are expecting a better security performance with additional frequency channels. So here I'm showing a kind of a model-based result based on phased array with 16 elements. So this is a linear array. And then, so we assume we are operating at 200 gigahertz with a pretty large bandwidth, 100 gigahertz. So, and then you can see in this 2D space where, I created, so it's at this 0, 0, this is actually where our transmitter is. This is Alice, and then this is Bob, represented by this triangle. And then, so with we actually didn't change our beamforming weight. So we just, put the faces to be 0 for all the antenna elements. And then and then the radiation pattern kind of changes frequency by frequency, so that with this large bandwidth transmission, we can obtain this blind region represented in this purple area. So in this purple area, eavesdropper will fail to detect one of the frequency channel. And as you see, this is actually a pretty significant region. So what I showed earlier here is, how we can achieve this nice physical layer property that the information theory initially asked for, right? So now we have this, like, how do we actually harvest that designed physical layer property to achieve security? So the thing is that we cannot just simply send, each of the message naively in each of the channel. Otherwise, eavesdropper would get most of the message except for one, right? So this is not secure. So what we are doing here is that we want to hide this message, and so that even when eavesdropper is getting something, it's getting the linear combination of the coded message. So then it's not obtaining the original message. So to kind of illustrate our idea here, I have an example of 3 frequency channel. So what you see here is that we are trying to send in the beginning. So this is, we want to send just one message symbol and then represent it by amp here. And then to do that, we kind of created 2 random symbols to hide that. So what it says here is that now we create this linear system with a different linear combination of this, message symbol and then 2 random symbol. And then we actually transmit X1, X2, and X3 in channel 1, 2, 3, respectively. What happens at Bob naturally is like he would receive all the 3, X1, X2, and X3, and then be able to convert the linear system back to the message and then the hiding symbols. But on the other hand, if the eavesdropper is in, she's in the blind region, and then we know she for sure is missing one of the frequency, what happens to her is that we can show this mutual information between her observation, which it's like we're giving her, kind of this luxury of obtaining the original symbol, even not with a corrupted noise. So we're assuming this eavesdropper getting the best observation she could with 2 channels. But then even that, the eavesdropper wouldn't be able to obtain any information about the original message, because this mutual information is 0. What it means is that the eavesdropper now can only randomly guess this message. So it's like, okay, I have no information, so the best strategy for the eavesdropper is to random guess. You might say that, okay, this is great. I mean, like, okay, you achieve information-theoretic security, but it sounds like this doesn't scale very very nicely with the number of channel, right? So we are now using 3 frequency channels, but then sending 1 message. And then imagine if we have 100 channels, do you still just transmit 1 message? This would be a horrifying scheme that doesn't have has a very low efficiency. So our answers to that is that it doesn't necessarily have to be like that. So the thing is that we're kind of introducing a different notion of security here, which is termed individual security. So what it does here is relaxing the security condition a bit. So instead from mutual information being 0, like the eavesdropper does not know anything about the message, to somehow a slightly different version. So it's given the observation at the eavesdropper, she would not know anything about individual message, not on all the message. So I want to give like an example to kind of illustrate what this idea is. So assuming that the eavesdropper observed this linear equation, so she observed that M1 and M2 is the same. And then in this case, you can think about it. It's the uncertainty of M1 and M2 individually still remain the same. Like in this case, the eavesdropper still has to randomly guess M1 and M2. I mean, like there is a relationship, meaning that if eavesdropper guess M1 correctly, then she automatically get M2 because they are the same. But for individual message, she has to randomly guess. So in this kind of security condition, security concept, individual security, then we could just like have a slight modification to our coding scheme to have an efficient, secure transmission. So with the same 3 frequency channel example that I showed earlier, so now instead of sending just 1 message, we will send 3 messages altogether. So what happens here is that like different messages are actually acting as the hiding symbol for one another. So there's one thing that's important here, that we need to make sure those messages M1, M2, and M3, they are uniformly distributed, and then they are independent of each other. So using this exactly the same coding scheme, what we can now show is the individual secrecy in the scheme. So demonstrated here is like we still allow the eavesdropper to obtain the best observation she could without any noise in 2 frequency channel. And then this information leakage to her is still 0. So, and then this is what, so this means that we achieve the individual secrecy. But also, as I kind of mentioned earlier, this doesn't mean that the eavesdropper has no information about the combination of the message. Indeed, the eavesdropper knows something about this linear system. It's just that the individual message, the randomness is still retained. So the next thing that we did, maybe it's naturally for experimentalists, right? So it's like we want to see how this would work in practice. So and then this is what we have done. So we want to have create this frequency in dependent radiation in actual systems. So what we do here is that we, although like in the earlier analysis, we kind of go for parabolic dish, phased array, but then in experiment, what we found in the beginning, like most obvious to me, is to kind of look at the diffraction pattern essentially. So this is what we have in the lab. So we have a horn antenna, and then we put something, a beam block in front of it to create diffraction pattern, which is known to have a frequency dependent radiation minima. And then we use 3 different frequencies here, like 100, 200, and 400 gigahertz. And then with measurement, we can see that the radiation minima actually change with different frequencies as we expected. And then these are the radiation nodes that's kind of spanning across the angular domain. And then with this setup, we transmit a kind of on-off keying transmission, and then see what happens to each of the location and the transmission. So as you can see here, this is the bit error rate. So so when in this angular domain, so Bob is at 0 degree, which is not shown here, but at 0 degree, Bob is actually doesn't experience any error. So the error is kind of error free in our experiment. And then you can see that this error would increase with as the receiver goes out of the main beam, and then also moving into the minima. As you can see, this bit error rate actually increase to the level of 0.5. And then there are also some side lobes, and then so you further see bit error rate going down, going up again. So and then we repeat this for different frequencies, and then we see that let's say if we look at the specific location, what happens? So in this specific location, you have for the blue frequency, which is 400 gigahertz, you basically, the eavesdropper basically doesn't see a change in her observation in this specific frequency, versus in the green and then the red, which is 200 gigahertz and 100 gigahertz, she still observed the RF keying transmission. But what happens here is that, remember, the scheme we are transmitting linear equations here. So it's linear combination x1, x2, and x3. And then what happens here is that at least at this specific location is x1 is not observable. So this means that we are achieving unsolvable linear system, and then therefore, this is the blind region that we achieved with only 3 frequency channels. Okay, so this kind of is our first attempt of realizing the absolute security, but then we also see there are challenges here, right? So like for sure, the first challenge, as I also kind of allude here in our experiment, it's like not all the antenna have pronounced minima as we want it to be. Just like the horn antenna, which we have in our lab, it doesn't really have pronounced minima. And then it's just not we have horn antenna in our lab, it's like horn antenna are actually deployed as backhaul links in our wireless networks, right? And then how can we kind of adapt those systems also to for our absolute security scheme? So from our experiment, we know diffraction would work, right? But then putting a beam block like this in front of it, actually it's not the best design as you can imagine, because it kind of block a lot of the energy by nature, and then although you create a nice radiation pattern, frequency dependent radiation noise, it inhibits the transmission like energy. So alternatively, we explore this other idea of what about we put a diffraction aperture in front. So we would have this kind of plate in front of our antenna, and then so it's a multi-slit aperture that will create a diffraction grating, and then that has a frequency varying minima. So this is what we did. We actually performed the experiment with collaboration with AFRL. So a PhD student, Yaz, had a summer internship with them and performed this very time-consuming but wonderful experiment. So what she demonstrated here is that with a four-slit diffraction aperture here shown in the picture, we see that we can create those radiation minima, and then those radiation minima does change with frequency. So meaning that this is like a scaling principle that we can use so that with more frequency, we would obtain a larger blind region. A second challenge that you might also have in your mind is that, okay, so you show me a significant large blind region before, but at the cost of a really large bandwidth. Like in the previous example I showed, I actually used 100 gigahertz to achieve like a significant blind region that I showed you. So the problem actually is like a constraint with kind of interaction with like a fixed antenna device and a varying wavelengths, right? So because our antenna has this fixed structure, and the radiation pattern only change as fast as how the wavelength is changing. So it's kind of fundamentally limited by how it's like fundamentally limiting how fast this radiation minima can shift with frequency. And I'm showing an example of what one could achieve with L21180, is like the Wi-Fi 60 gigahertz, like the standard defined bandwidth. And then it's not looking very promising because, as you can see, like the lowest frequency data tone and the highest frequency data tone, like representing in red and blue here. So the radiation minima is only separated by 1 degree. So it's kind of saying, okay, it's nice you have this absolute security scheme, but then you can protect 1 degree of your transmission. This sounds very depressing, but there are things that we could do here. So what I think would be the way to go is that we could use the digital beamforming architecture here to have a frequency, a kind of subcarrier based beamforming pattern design. So I'm showing here 2 architectures. So one is analog, one is digital. So in the analog beamforming here, we have just 1 RF chain, and then once you decided what you want to transmit with and in different frequencies, they go through, like each frequency, they are going through the same kind of phase and amplitude change, and then transmitted by the antenna. And then in this design, this is what I called, it's like the fundamental limit of what it's like the behavior is limited by how fast your wavelength is changing. But then on the other hand, so in this digital beamforming architecture, so in each of the frequency, you can actually control that, okay, so for the red one, I want to have some certain, phase and amplitude relative relationship between, this antenna versus that antenna. And then this relationship can be different, per per frequency. So the red frequency, it's having a certain beamforming weight, and then the blue frequency is applied with a different beamforming weight, and thus it can have very different radiation pattern, and therefore a radiation minima at dramatically different locations. So it is actually not a very difficult process. I mean, what we try here is something very simple. And so we can zero force based on pseudo inverse of the channel, and then to place the radiation minima to the angle that we want. And then for each of the frequency channel, we want to assign it a different minima, right? So frequency 1, please zero force to this direction. Frequency 2, please zero force to another direction. And then the way that we assign this minima is simply uniform distributing in this orange zone that I show here. So it's that we have our bob located in this angle, and then we know that we wouldn't be able to zero force to a location that is very close to bob. Otherwise, bob also suffers from SNR loss. So what we do is we zero force to the region outside of this clear zone, just by uniformly choosing these angles. And then what we see is really promising, that with digital beamforming, and then so we have 4 antenna linear array here, and then 4 RF chain, and then the blind angles that we can achieve increase much faster with the frequency channel. So the orange one is representing analog beamforming, where we only have 1 RF chain. And as you can see here, this is actually the point where all the kind of data tones defined in the AL2.11 AY is used. So in one case, like when we are using digital beamforming, we are able to achieve a much larger blind region, so around bob. So this is basically this region around bob. We are not able to create. We are not creating minima there, but outside that zone, like most of the part, we can cover with kind of a digital beamforming method. And versus if we don't have that, this is kind of that miserable 1 degree that I showed you earlier. So this is our kind of journey of reimagining how physical layer security and information-theoretic based security can be redesigned with the effort from from the physical layer, and then also a joint effort from network coding. So we are continuing our research in this direction, and then there are some exciting things happening now. First of all, so what I showed you earlier is, like we are having a high hope of this digital beamforming would be a great combination for our absolute security approach, and we want to realize it in experiment. So the plan is that we want to have absolute security implemented using this pi radio system, which is at 60 gigahertz, and then has a 4-element linear array. And then so what you can see here is this is the pi radio node, and then it has a transmit antenna and a receive antenna array. And then so for the transmitter side, it has 4 elements, and then for the receiver side, it also has 4 elements. So we are gonna, just like activate the transmitter side to realize the digital beamforming, and then showing this how this radiation minima will be changed over different subcarriers. And then the second part, which I think it's also quite unique in a lot of wireless security experimental demonstration, is like a lot of times, like in experiment, we can demonstrate, let's say, SNR, we can demonstrate bit error rate, but it's not as usual that we dive into kind of the fundamental like definition of information theory, right? So what we want to achieve here is an information theoretic security. And then so the goal here is also we want to demonstrate information theoretic security experimentally. So that requires us to estimate mutual information leakage from our data set. So this is actually not a trivial process. Like mutual information estimator is a area of itself that, because a lot of different like applications rely on estimating mutual information. So what we want to do specifically here is that, for example, we do let's say a transmission like this, with our coding, and then with different attenuation in different frequencies, right? And then we want to see how much information is leaked to the eavesdropper, that's and therefore we want to show that there is no leakage information wise. And so this is kind of a separate concept from decoding, right? It's like we want to demonstrate almost no information leakage, and then by that it automatically tell you that it's not possible that this can be decoded, right? It doesn't work the other way around. It's like if there is information leakage, you still need to find a way to decode the system. But what we are trying to prove is something stronger, that there is no information leakage that the eavesdropper can exploit. So here are some references if you are interested in our research. And then, so I want to say this is not possible without like a very interdisciplinary team. So for this project, we actually have like a joint effort from MIT, Brown, Rice, Technion, Clemson, and UC Leuven. And these are all my wonderful colleagues here. So in summary, what I share with you is our new journey of searching a different way of realizing security in physical layer and combined with network coding. And then our security scheme doesn't assume for a specific eavesdropper locations. We want to achieve this for a large region. And then our scheme actually comes with an advantage with no data rate penalty. And I also show you in physical layer how the different ways that we can realize frequency-dependent minima to address different challenges, like, for example, to modify existing antenna for the desired physical layer feature, or to reduce the bandwidth required to achieve large blind region. So I would be happy to answer any questions.
Thank you, Chia-Yi. Yeah, it was a great talk, and yeah, of course, I enjoyed it. And thank you for that. And now we are open for the questions. So we have right now a question from one of the audience. Let me just, okay, we're getting more questions now. So the first question is, usually when it's from Sid Dongre. So he's asking, usually when digital beamforming is used to zero force almost all directions except for a few where Bob is located, there is a significant reduction in the SNR at Bob. Did you proposed digital beamforming scheme impact the SNR at Bob?
Sure, this is a very legit consideration for digital beamforming. So as you might recall in one of my earlier slides, we want to kind of we know that if we are beamforming to a channel that is very correlated to Bob, we are hurting Bob's SNR. So the most naive way that we are doing here is that we are not zero forcing to locations that are very close to Bob. So this is kind of a fundamental limit that we wouldn't be able to, without hurting Bob, we wouldn't be able to kind of have null very close to Bob. And then so you are right, and we do take Bob's SNR into consideration, and then this is how we do it.
Okay, thank you, Chia-Yi. So there is another question. It's based on, so it says, it's from Anik Malik. So he's asking, zero forcing based beam steering techniques have been known for sensitivity to noise. What has been your experience with this kind of noise?
This is a wonderful question, because this is also something I thought of like when I designed this zero forcing based radiation minima theory. So what happens is that, so I don't have that result, in this particular presentation, but I can share what I observed kind of. Okay, so the thing is that, how do I take into kind of the sensitivity to noise? The way that I explore kind of numerically is I first have this zero forcing beamforming weight applied. And then I actually don't assume this weight is perfectly applied. It's actually applied with some variation, with some noise added to it. So it's not a perfect beamforming weight. And what I observe is that the location where where the null happens doesn't change that much. What change is the depth of the null. So once you have a higher noise, the depth of the null is not as strong. It's kind of going from very deep into a higher degree. So I think this is also some kind of fundamental limit. It's like we need maybe like a very precise beamforming architecture to achieve a deep null. But I think we can still realize the radiation null direction pretty well.
Okay, thank you, Chia-Yi. So we have one more question from Hanif. Hanif, would you like to ask the question yourself and meeting?
Yeah, sure. I'm following this discussion about the beamforming, and beamforming, as everyone knows, assumes the CSI or channel set information at the specific location, specifically at Bob, and tries to then invert the channel to basically nullify the signal, everywhere else. But it is, when we discuss about an absolute security notion, there could be other points around the transmitter, not necessarily always close to Bob, that might have a similar CSI, by accident or by random. And then what we try to achieve at Bob would also be happen there. Like if you don't want to nullify the signal there at Bob, it would not be nullified on those places, or other so on and so forth. So then basically I'm wondering, whether you have experimentally evaluated the scheme on the different channel scenarios. From information theory perspective, sometimes we assume that the location transfers to always a direction, and there is no other point in the region that has very low correlation, CSI with the location of Bob. But in practice, depending on the type of channel model and the environment, that might not be the case. So I was just wondering if you have also experimentally evaluated the scheme on there, in different.
Yes, this is also something like I think of a lot. So thank you for asking. So this question get into the bottom why we consider absolute security scheme for millimeter wave and terahertz network, not sub 6 gigahertz, right? So the thing is that our analysis is largely based on line of sight analysis, as you can see here, and then our experiment, because it's in millimeter wave and terahertz, and then they are also largely it's like strong line of sight. I can I totally agree that if we have a multi-path environment, then we would observe things very differently, right? So in, let's say, in sub-6 gigahertz, we would not observe what we see, you know, in this kind of blind region. It would actually be more like a scattered thing. It's like, oh, this channel is correlated with Bob, and then that channel is correlated with Bob, and then those points are kind of scattered in space instead of kind of centering only around Bob. I don't have experiment to support that, but I think that will be what happens here. And then I do think there is a kind of a preference for the scheme for a stronger line of sight system, because those multi-path, what it essentially means is also that it's enhancing signal. Basically, it's like once you have multi-path, you kind of have a virtual transmitter that is radiating in space, and then that's kind of content with our intention of having a low signal in a specific space, right? It's if we have strong multi-path environment, it's really hard to get a space, a location in a space to a very low noise, very low intensity, like so that's kind of a fundamental challenge associated with multipath. Yes.
Thanks.
Okay, so there is one more question from probably
It's
from
me
Manu.
again.
Yeah. So you want to ask one more question, or?
Okay, so since we have time and there's no more question, I ask my second question. So in the very first slide, I mean, you showed us encryption versus physical layer security, and it could be a very typical question that you might have answered already 100 times, and you may need to again answer in future talks, and that is if you can elaborate a bit about what are those applications or scenarios perhaps that encryption is not enough or not useful or not strong enough, and therefore we need some physical layer approaches for.
I think this comes from a kind of fundamentally different perspectives, right? So I think for the encryption, the validation of such system is coming from, okay, this is a very hard process in reverse. So then therefore, if you don't have, because building on the non-existence of an efficient way to reverse the problem, so then you get the security. So I think what physical, it's like information theory based approach, that means put it in a more general way, is when when those assumptions are validated, right? So if eavesdropper actually has, let's say in the future, let's say 10 or 20 years from now, and then someone discovers this clever algorithm where you can invert the process, or coming up with like the actual implementation of quantum computers that can break the proposed encryption systems. But even in those scenarios, information-theoretic approaches would not fail. So I think that's one very important intuition why we want to explore information-theoretic approaches. And I think like what we're doing here is to kind of combine this and then see how this can be achieved in wireless network, combining with physical layer design.
Okay, so we have one more question from audience. It's from Moon Talukdar. So she's asking, as a linear technique, zero forcing might struggle with mitigating inter-symbol interference in certain situations. How you tackle this issue in your experiment?
Okay, so when you kind of this question get into kind of experimental implementation and then related specifically to inter-symbol interference. So what I am trying to do in the experiment here is more like an OFDM-based system. So then I can have frequency-dependent operation in each of the subcarrier. And then, so for OFDM system, we know that the symbol interference is dealing somehow managed by, you can add the cyclic prefix. So that's something, I mean, if I see inter-symbol interference, I can employ those things. But I'm actually still trying to implement. I haven't had experimental data yet, so I'm not sure to what extent how much, like, let's say, cyclic prefix is needed.
Thank you, Chia-Yi. So as we don't have any more questions and we are kind of running out of time, so in the interest of time, we can probably conclude our talk. And thank you very much for the wonderful talk, and thank you for engaging the audience. And we also thank everyone from the audience for joining, and hopefully you enjoyed our talk, our initiative. Hopefully you like it. And we are going to have more such talks. We are going to have the next one in the middle of December. And so thank you. And Chia-Yi, good luck for your job search this year. And yeah, so with that, we'd like to conclude, and have a great rest of your day and week. And see you in the next talk.
All right. Bye.
Thank you. Bye-bye.